Okay, so we have the pleasure to have Nikole visiting us today. She's an expert in planetary science, particularly the characterization of atmosphere in exoplanets. She has a very interesting journey, so you should really talk to her, find time to chat with her. Maybe she has still a couple of slots available later. So she has done her PhD in University of Arizona in 2012. Then she joined the technical staff in Charles Stark Draper Laboratory. Then went to staff scientist in Boston University. Then a second postdoctoral fellow at MIT. They joined the Space Telescope, becoming the exoplanet group leader, working group lead in the Space Telescope, then a program scientist for JWST in the same institute as associate astronomer, and then joined Cornell as a deputy director for Carl Sagan Institute, and then she's associate professor now in Cornell. And we are very happy to hear now about deep reconnaissance of exoplanet atmospheres with JWST. So take it away. Thank you.
Thank you. All right. Hopefully people online can hear me. I know this is kind of a small crowd, but feel free to interrupt with questions. I also know it's a small crowd because it's election day. Yay. Again, I had not put 2 and 2 together when I was like, yeah, that's a great day. I have voted, don't worry. Hopefully everyone else in the room who is going to participate in the election has already voted. I will give you an opportunity to do a much more fun election in just a moment, okay? All right, so I'm going to talk mostly about JWST and all the amazing exoplanet science that it's done. But I can't talk about JWST without first showing you beautiful pictures. All right, who has this as like the background of their stuff? Okay, Zoom screens. I love this. I see lots of people with this behind their Zoom heads. It's absolutely gorgeous. And I think one of the things that I want to emphasize is that, so we've zoomed in on a little bitty part of the JWST field right here. So this is that same image. This is what the same image looked like from Hubble. Okay. It is a gigantic leap forward going from Hubble to JWST, and that's not just for beautiful images. I mean, Hubble has had the game on beautiful images for 2 decades now, but also it has increased our ability to do spectroscopy in a broader range of contexts. So great for pictures of beautiful nebula, etc. Also great for thinking about how this has changed in the mid-infrared. So those Hubble images, remember Hubble only operates out to about 2 microns. Okay, it doesn't have any cryogen. It really can't go past that, otherwise all you're seeing is the telescope. It's in orbit around the Earth. What this means is that JWST has really become our first sort of relook at wavelengths longward of 2 microns. I grew up doing Spitzer. This was my baby. Okay, this is what I did my dissertation on. But you can see already, going from Spitzer, this is the IRAC 8 micron channel, this is JWST MIRI, same field. Huge advancement in terms of resolution, both spatial and spectroscopically. All right, now let's start with planets in our own solar system, just ever so briefly, and in part because I'm trained as a planetary scientist. It means I was trained on solar system objects, and then I started applying all the things I learned about beautiful planets like Jupiter to exoplanets. Here is a Hubble image, all right, beautiful. Here is a JWST image. Now, maybe not as dramatic, but you can see, of course, a lot more detail in these clouds right here. And in particular, what you're seeing is because JWST is probing Jupiter at infrared wavelengths as opposed to these beautiful optical wavelengths, you can see much deeper into the atmosphere. So actually, if you look right here, you're seeing quite deep into the atmosphere where we can take measurements of different chemical species, methane, and possibly get some interesting details about water. The other interesting thing that people sometimes overlook is to see it's glowing right here. All right, who saw the aurora recently down here in NYC? No? Oh, I should show you my picture later. So my husband was flying from JFK to Ithaca the night of that beautiful aurora were happening, and he snapped a couple pictures. Asked me about it later. But these are aurora on Jupiter that you can see glowing at those near-infrared wavelengths. All right. So now I wish I could take beautiful pictures of my exoplanets in the same way that we take beautiful pictures of Jupiter. But that's just not happening. These things are, of course, very far away. They're also very dim compared to their host stars. Now, I primarily use a technique called time series observations, where we actually disentangle the planet's light from the star's light, not spatially, so I don't block out the star's light. Instead, I use time to tell me which part of the light is the planet's light and which part of the light is actually the stellar light. Okay. And so the way that this works looks something like this. So we have an exoplanet. We're assuming it's on a very short period orbit. Most of the planets that I study have orbital periods of less than 10 days. And so we assume that it's tidally locked, just like the moon is tidally locked to the Earth. And what we do is we watch as this planet goes around in time, and we monitor the flux from the combined light of the planet and the star. And one of the first big things we see is when the planet passes in front of the star, it blocks some of the star's light. This is called the transit. This is the way that Kepler, TESS, and lots of other facilities actually detect exoplanets. It makes about a 1% signal or less on average. Now you can keep watching, and you can actually see variations in this combined light as you start to see more and more of this hot day side of the planet. These are phase variations, and I'm not going to talk too much more about today, but feel free to ask me about later. And then we have something called a secondary eclipse or an occultation, and this is where the planet ducks behind the host star, and we lose the light from the planet, but that allows us to tell us what part of the combined light is from the planet as opposed to the star. Okay? Now, when we had Hubble, which I love Hubble, but it was not great for a number of reasons. It is in orbit about the Earth. It goes around every 90 minutes. And so if you're trying to do an observation that's 5 to 6 hours in length, you have to go and capture a bit of the observation, then duck behind the Earth, a bit of the observation, duck behind the Earth, a bit of the observation, duck behind the Earth, and here's where the planet is transiting the host star, and then we come back here and it's gone past the host star, all right? And so this doesn't look like much by eye, right? It has all sorts of systematics. You have these huge gaps in the data due to the fact that the Hubble is being occulted by the Earth on a fairly regular basis. In fact, there's so much systematics in this first orbit right here, and this is because you actually get this charge trapping, and then actually the telescope is heating up as it goes around in its orbit. We don't even use these data. We just throw it all away, okay? So this is what transiting exoplanet observations look like with Hubble. You can still get information out of that. You are able to fit a basic model for what the system should look like that runs through your sparsely sampled data points here, but you get zero information on what we call ingress and egress of the planet, okay? But this can still give you relevant measurements. And then what you can do is you can actually spread that light out using a prism or grism or whatever spectrograph you may have, and look at how that transit depth changes as a function of wavelength. And so what we do is we actually measure planetary radius as a function of wavelength. The bigger the planet appears, the more opacity it has at that wavelength. And we can tie that back to things like, does it have sodium or potassium, clouds, water, etc. Okay? And so that's what we do. We use time and wavelength to measure how a planet's size changes, okay, as a function of wavelength, and to monitor the system as a function of time. All right. So, with Hubble, we were able to study a lot of planets like this WST 96b. This is what we call a hot Jupiter. So this is roughly a Jupiter-sized object. It has a temperature of close to 2,000 degrees Kelvin, though, so nothing like Jupiter, all right? This one has been heated up. You can see all its water, which is great because when you use Hubble, you're able to then measure these water features to about 1,000 parts per million precision. So these are water features in this planet's atmosphere as observed with Hubble. You're also able to use a variety of ground-based instruments. Here we're using BLT4's observations to capture the sodium line, which is really strong right here. Okay? And so we're learning something about the alkali abundances in this planet's atmosphere, and then also the amount of water that's in its atmosphere from Hubble. Okay. Now, JWST, in its early release observations, so these were the first things that were released to the public back in July, I don't know if anybody remembers that, in 2022, looked at the system again. So this is WST 96b, the same system that was being looked at with Hubble. Here we have an observation using JWST. Now JWST is not parked around the Earth, it's not orbiting the Earth, it's way out at L2. This is great. That means the Earth is not getting in the way every 90 minutes, and you can capture the entirety of this planet's transit. So this is the starlight blocked by the planet. This is the actual data, right? So big difference from what I was showing you before with Hubble. And we can again turn that into a spectrum by just again measuring the size of the planet as a function of wavelength. And again, we see these beautiful water features. So water everywhere through here. Not a drop of strength though. Of course, this is a hot Jupiter. And we've seen basically a 5-fold increase in the precision from one observation. So that is the HST observation from before. We had to take 3 different observations. Okay? We've managed to get 5 times better data with one single observation with JWST. And that's, I can't show you beautiful pictures of my planets, I'm sorry, but I can show you beautiful spectra and emphasize, yeah?
You keep saying water, but you said it was 2,000 degrees Kelvin.
Yeah, water vapor.
Oh, water.
Yes, so water vapor. That's the nice thing, is so Jupiter has all of its water locked up in those clouds. It's really hard to get at the water in Jupiter, and for us to understand water abundance is there. Hot Jupiters freely show us all their water because it's all in the vapor.
It doesn't associate.
So you start to dissociate water on the day side at around 2,300 Kelvin. So some of these do actually show water dissociation on the day side, so they're atmospheres. Okay. All right, so here's my beautiful spectrum of the hot Jupiter WASP-96b. Now, let me get to the core of it. So hopefully I've motivated that JWST is going to do awesome things for exoplanets. I was put in charge of 130 hours of what's called guaranteed time observations that were intended to sort of push the limits of what JWST was capable for exoplanets. And so the program that we designed decided to take all of our 130 hours and dump them into 3 planets. We looked at a hot Jupiter called WASP-17b, a warm Neptune called HAP-P26b, and then a temperate terrestrial planet called TRAPPIST-20. Now that time wasn't evenly distributed between these 3 planets. We spent most of our time on WASP-17b, and I'll show you why in just a minute. But we were hoping to use these as basically archetypes of the types of spectra we might expect for these types of planets, both in transmission and emission, that would either guide further observations of these planets or actually help people to understand how to observe other similar planets with JWST. All right, now at the end of the talk, you get to vote. You can be Team WASP-17b, Team HAP-P26b, or Team TRAPPIST-1e. So listen carefully and decide which of these that you think is the most interesting and exciting. All right?
What is the little b next to 17?
So little b. So WASP-17, big A is the star. WASP-17b is the planet. Okay. So that's how we name things. It's very creative.
And what is the WASP and TRAPPIST?
Yeah, so WASP is a survey, ground-based survey, and so all of the planets, when they were discovered, that ground-based survey, you got a variety of numbers. I think they're up to like WASP 300 and something now. They've discovered many planets. HAT, also a survey, ground-based survey that detected it. So it was the 26th planet detected with the HAT survey. TRAPPIST is interesting. So TRAPPIST is also part of a ground-based survey, but it's the only system that was detected with the TRAPPIST telescope. It was actually a precursor to something that's called speculos now. So there's another survey. It was targeting very cool stars and looking for rocky planets. So these are all surveys. They get surveyed among yours, just like Kepler and TESS, etc. All right. So I didn't do this by myself. I'm just going to throw that out there. 130 hours is a lot of time to plan and process. We have a team of about 30 scientists, most of them early career, scattered around a few key institutions, including Cornell, MIT, NASA Goddard Space Telescope, and JHU APL, and the University of Bristol. And so this is the group that has been working diligently on doing both data analysis, observation planning, data analysis, and then also theoretical modeling to interpret our spectra. All right. So let's start with WASP-17b. So this might be your winner, I don't know, but let's see how it goes. All right, I like to call this set of observations the JWST Hot Jupiter Deep Field, because I'm going to borrow from my cosmologist friends, all all right? We spent a total of 70 hours observing this target, so akin to a deep view. Now, we collected data spanning 0.6 out to 14 microns, and we did that in a series of 6 observations. We can't get 0.6 to 14 all in one go. We had to use the JWST nearest instrument, near spec and mirror instrument, but we got both the transmission, so when the planet passes in front of the host star, and the emission, where the planet passes behind the host star. Now the interesting thing here is that the transmission is probing along the limbs of the planet, so right along these edges, this transition between day and night, so you can think of it as sunrise and sunset, whereas the emission is probing just the hot day side. And so that's where you get these fun effects where like water might be in one place but not another because it gets so hot and probing down. Okay. All right, so let's start again where we were before JWST. These are observations, transmission observations of WST-17b. So this is transit depth in percent. So you can see sort of we're looking at a 1 to 2% signal. This is from Hubble and Spitzer. So here we have Hubble observations out here. Here are these 2 data points. Those are the only 2 data points we had from Spitzer. We have so many planets with just 2 data points from Spitzer. And this was a study done by a member of our team pre-JWST data coming down. And we were able to fit a rough model here. We knew that there were probably some aerosols in its atmosphere. We're seeing scattering out towards these shorter wavelengths. And these 2 data points were telling us potentially there was carbon dioxide. It's hard to say. There's a lot of stuff mushed into that 4.5 micron point. And that meant that the planet was perhaps enriched compared to solar or stellar values. Okay? In our own solar system, Jupiter is a roughly 3 times solar values. Saturn is 10 times solar, and then we have Neptune and Uranus that are sort of 30 to 50 times solar. And that tells us something about their formation history, and so that's why we care about these things.
I'm sorry, I was thinking about something else. What is it that's N times solar?
The overall metallicity, so everything
okay,
except
okay,
hydrogen and helium. Yeah. All right, so here we have the JWST observations. Now, strangely, they fell right on top of that model. So Hubble and Spitzer were not doing a terrible job of predicting what we should see, but you're getting a lot better resolution of what's happening here. You're actually able to pick out spectroscopic signals by eye, CO2 being one of them. So before that was just one giant point that could have been carbon monoxide or carbon dioxide. We of course have water, there's all this water vapor right here, and then more water out here. Now, one of the first things we saw when these data came down, and we actually got all of these data within the span of about 3 weeks, it was kind of rough, is that there was this weird thing right here. All right, so let's get into the weird thing right here, and it's always about where it's different. So the weird thing right there, the weird thing out in this region here, around sort of 8.6 microns, is where you might expect to find a stretch feature from silicon dioxide. Okay. Not in the vapor form this time. This is actually basically quartz crystals in the atmosphere of this planet that, when they interact with the light, are giving this signature at this very specific wavelength right here. Now, these quartz crystals, this sand, more or less, were not predicted to form in exoplanet atmospheres. We had long been using sort of the clouds that form in brown dwarfs as sort of what we should expect, and so we would have seen something like instantite or forsterite. But instead, we were seeing these quartz crystals, and we were seeing that they were really teeny tiny. So these were like quartz snow, teeny tiny. And this was telling us something about the way...
So how do you know they're teeny tiny?
Oh, so the teeny tiny bit is because we have data all the way out here, and so we can use the Rayleigh scattering slope to constrain the size. Yeah, and also this feature would get broader the bigger they are. So the fact that it's this size right here means that it's very close to that same sub-micron size. Okay. So we have found quartz crystals in the atmosphere of this planet that were not predicted. They're small, also not predicted, and so that's indicative of some of the dynamical processes in this planet's atmosphere. And I'll get back to in a minute that we think these are actually forming more sort of on the night side of the planet and then being transported to the day side where we see them.
Can you estimate how old the planet is?
So these are all old planets. These are not young planets. So we use this, basically the stellar age as a proxy. So
Which is?
I think it's close to solar age. So yeah. Okay. So We started looking at other planets, so I'm going to divert from WST-17 for just a minute and introduce you to another planet called HD 189733b. Okay, this is actually one of the first 2 transiting exoplanets discovered. It's been highly studied. And when we went and looked at its day side atmosphere, so we're looking at that hot permanent day side with the same instrument, this is the MIRI LRS, we saw those same signatures. See this spike right here, except now it's upside down because we're looking at absorption as opposed to transmission. Okay, so here this is absorbing, the other ones this is absorbing. Okay, and so we're seeing that same very sharp feature that's due to these small particle quartz crystals at planets that are not the same temperature. So HD 189733b is much colder than WST-17b, but we're seeing these sort of ubiquitously across the hot Jupiter population. All right, so let's get back to WST-17b momentarily. Let me focus in on this region right here, which is littered with lots and lots of water. And we had a paper recently accepted that made what we call a definitive water measurement for this planet. The previous data, which was the JWST and Spitzer data, we used our atmospheric models, and so we use our atmospheric models in a Bayesian framework, we call it atmospheric retrievals. You can ask me about it later. But basically we throw 1 million models at it and see which ones actually match our data, and that allows us to infer how much water or methane or CO2 is in the planet's atmosphere. Now the Hubble data and the Spitzer data kept giving us this bimodal solution. So the planet was either super water rich or it was completely water poor, depending on what other combination of things you mixed in there with it. Now that we have the JWST data, we have this very nice posterior distribution right here that shows that the water abundance is in fact what we call supersolar, so -3 is usually what we call solar. And so this planet is enriched in water in comparison to its star.
But it's still bimodal, right?
So these right here?
Yeah.
No, so there's 1, 2, 3, these are 3 different reductions, and so you get slightly different answers depending on which reduction you're using.
Is there a tension between the 2 data sets?
This one and this one? No, if you throw, so once you add in the nearest sauce data, if you throw them all into the same bucket, you get this. Okay. It's just that these data did not have the same wavelength coverage. So remember, it only covered sort of here to here, all right? It was missing all of this stuff out here. And so it was not able to get a handle on the distribution uniquely.
So it's what we could call it the H2O tension.
That would be another good one to borrow. I'm going to borrow that one later, the H2O tension, yes. All right, so WST-17b, I'll keep going here. All right, let's look at this region right here. This is our near spec data. We got a booming CO2 feature right there. But in addition to our booming CO2 feature, which was not actually predicted for hot Jupiters early on. So if you make a planet that is sort of the same composition as Jupiter, so 1 to 3 times solar metallicity, you will not get carbon dioxide as the primary carrier. You'll get it as carbon monoxide. And what we've seen over and over again, and I'll show you this later, is that CO2 seems to dominate many of the spectra that we're seeing in exoplanets. We can tie this back to sort of where they formed in the disk and also how they accreted planetesimals, so that's all very interesting. Now, in addition to this booming CO2 feature that allows us to get a really nice handle on the overall metallicity of the planet's atmosphere, we saw a little thing right here. So you see, here's our model, this gray line. It doesn't quite match. And again, I didn't fit this model to the data, let me just say that. That's just the model that was predicted from the Hubble and Spitzer data alone. Now, sulfur dioxide is a photochemically produced species. It doesn't occur sort of naturally. It's not something that just comes out of the mix. You have to have basically UV photons coming in and creating this chemistry, and SO2 is a byproduct of that. It's thought for a long time that a planet as hot as WST-17b, which is around 1800 Kelvin, could not sustain photochemical species. So it's thought that they should break down pretty rapidly and go back into equilibrium. So the fact that we're seeing SO2 is really interesting and means that we need to update our photochemical models to consider the possibility of such species persisting in this planet's atmosphere. All right, so beyond all of that, we also have Hubble observations using this mode, it's G280. The whole story here, that's a whole other talk. This is a mode, this is what happens when you read the manual. I was reading the manual one day and I'm like, why is nobody using this prism? Apparently the cosmologists didn't want to use it, or nobody used it. Turns out exoplanet science loves using this thing. It gives you broad wavelength coverage in the UV. And so we have a legacy or a treasury program on Hubble that's gathering spectra in the 0.2 to 0.9 micron region for this planet and others that will allow us to finally nail down sort of this part of the spectrum, which is related again to the average particle size of those clouds. All right, let's get to the emission. All right.
Can I just add, the SO2, is that coming from the surface of the thing?
This is a gas giant planet, so
Yeah,
it
has no surface.
it has no surface. So the SO2 is not volcanic. It is being produced in the atmospheric chemistry due to UV photolysis. Okay. All right. So before JWST, this was the sum of the emission spectrum from WST 17. Those 2 data points. I've drawn you some black body lines just to draw your eye here. This is eclipse depth in parts per million, so this is the kind of signal we're looking at here. All right, we knew that the planet was somewhere around 1800 Kelvin on the day side, but other than that, didn't know much anything based on the measurements that we had. Then we went and got emission spectra using, again, those 3 modes, near SAS, near spec, and mirroring. That more or less follow that 1800 K black body line, but deviate significantly in a couple areas, which is interesting. So let's break this down a little bit. All right, so what I've done here is I flipped this into something called brightness temperature. Okay. So we have a flux of the planet over the flux of the host star. We can assume some sort of either black body or stellar model for the star. And then we can turn that into a sort of predicted black body temperature as a function of wavelength. Right? This is much more useful for my planetary theory brain, okay? Because it's telling me the temperature of the photospheric region I'm probing with different wavelengths. And so down here we're probing roughly around 1750 Kelvin. We see features from water and CO here. Now we predicted a much stronger CO2 feature down here. And it's much weaker here, and that's a product of basically the thermal structure of the planet. We see water all throughout here, and then the planet goes wacky right out here. All right. Now the planet is not necessarily 3000 degrees Kelvin. We think that in fact we might be seeing a contribution of reflected light. So those wavelengths are such that you can start to get light reflected off the planet into the signal that you're measuring. But it's also possible that this planet has what we call a very high internal temperature. Now the internal temperature is usually related to some sort of formation or migration history. This planet is on a wacky upside down retrograde orbit. So however it got into its current orbit, we don't think it formed there, it probably did a whole lot of machinations with other planets in the system, which could have led to the fact that it has a very high internal luminosity. It's also very puffed up. So it's almost 2 Jupiter radii in size. And so we are in the process of trying to tease out which of these 2 scenarios would make the most sense. If we look at the data and we assume that it's all from reflection, we get a sort of a geometric albedo for the day side of the planet at about 0.2. It's a little high, but not unheard of. Okay, so it'd be very shiny. Again, we have those quartz clouds that we know are along the limb of the planet, and so possibly those are contributing to reflected light on the day side. Now, if we, again, look at different scenarios on how to fit it, here we have models that run through the data, but they do some wacky stuff with the pressure temperature profile, and that's what I'm showing over here. So we have pressure on the y-axis and temperature on the x-axis. And what the models want to do is that they want to basically create a very hot interior right here, and then open sort of an optical window, so it sort of gets rid of all the alkali absorbers and lets you stare directly down into that deep hot layer below. Okay. Now with the current data that we have, we can't actually disentangle these 2 scenarios, but we're in the process of actually obtaining hopefully some shorter wavelength data that will allow us to tell the difference. All right. So thank you for bearing with me with all of that data, 70 hours. On WST 17b, We now have a full transmission and emission spectrum, but we're not going to stop there. So this is maybe why WST 17 should get your vote in the end. What we're going to do is take those very, very nice data, which the transmission, again, are probing the limbs of the planet, and the emission data are probing the day side of the planet. Okay, so again, we have the transmission, we pass it in front, and the emission when it's behind. And what we're going to do is we're going to stop treating the planet as a uniform ball. So all of those models that we ran, we assumed sort of a 1D atmosphere, pressure, temperature, chemistry. We assumed that it had the same composition throughout the whole day side and basically the same temperature. All right, but in reality, this is one of my GCMs, exoplanets probably look something like this. All right, they have temperature gradients as a function of latitude and longitude that we should be considering when we're doing our atmospheric modeling. So one of the big things we need to consider is that very often the hottest point of the planet is not located at the substellar point. We've known this for a while, okay? We've known this from Spitzer. The reason is because there are roughly 1 to 2 kilometer per second winds in a jet stream around the equator that are transporting those air parcels that are heated at the substellar point downwind. So that tends to shift everything to the east. So this is what we call a super rotating jet. Okay. We also know that you have this jet's also carrying cold air from the night side. That might be laden with clouds and other aerosols. And that it's then transporting that same air across this hotspot and then back onto the night side of the planet. And so we can figure out a lot of the interesting physics and chemistry that's happening in a hot Jupiter atmosphere if we can tease apart what's happening on each of these limbs and then also on the day side of the planet.
I'm a little confused about the geometry. Where is that star?
So the star is, you are the star.
Oh,
You are the star.
It's phase locked, right?
It's phase locked, yeah.
Okay.
So this is you staring at the day side.
and what did you say? I just apologize.
No, it's okay.
I just, I'm reading a picture. What is the red bar?
So this is the hot spot. So normally, if there were no strong winds,
Oh, that's.
you just have all your heat deposited right there in the middle, right? High noon would be like hellscape. But instead, because there's strong winds, it tends to transport them and string them out in this sort of blobby thing. All right. So we've been developing techniques for a while now. These are various members of my group and other groups to do what we call both transmission mapping and emission mapping, or eclipse mapping. Eclipse mapping has been around for a little bit longer. We were able to do it exactly once with Spitzer, right? And what we're doing is we're actually taking, again, that observation where the planet ducks behind the host star, okay? And if you don't assume that the planet is uniform in temperature, it will actually imprint signals on the ingress and egress of your observation that can then be disentangled to tell you something about the spatial distribution of temperatures on the planet. Now these are tiny, tiny signals on top of another tiny, tiny signal, so keep that in mind. For transmission mapping, again, we are taking advantage of the fact that the planet, depending on the opacities along each limb, will appear larger or smaller. Okay? So if you have a bunch of clouds on one side, it's going to appear bigger at those wavelengths that interact strongly with the clouds. If you have a bunch of water on one side but not the other because maybe it dissociated, then you're not going to see the planet be larger on that side. All right. So, from our WST 17b observations, right, here are our transits. By eye, they look identical. Right? Everyone by eye can tell the difference between these two. These are focused in this region out here that's probing, again, these silicate clouds. This is focused on this region right here, so we've summed them up. This is really focused on those water features. Okay. Now, if we fit one of these models that doesn't assume that the planet is a sphere, uniform temperature sphere anymore, we can see that these two regions actually give us different shapes, right, and different sides of the planet being larger than the other. So we can actually map the planet radius, or opacity if you want to think of it that way, as a function of degrees longitude, more or less. Okay, so we're mapping this out. These are all sort of the allowed solutions in the region. All right, and so here we have, again, our water. We're seeing that the evening terminator of the planet appears bigger at the wavelengths where water is probing, so it's just hotter. And then when we look at these wavelengths that are probing our silicate grains, we see that the planet looks bigger on the morning terminator. And so we know that those SiO2 clouds are actually confined to that morning terminator. They're morning clouds. And that actually means that they likely formed on the night side of the planet and are just being entrained in that very fast jet stream that's coming along. And then they've dissipated by the time they've reached over here, where we're seeing that very clear water signature. Okay? So we've managed with these data, because they are both emission and transmission data, and because they are such high precision, we've been able to map out clouds and where they are on an exoplanet atmosphere. Right. Now, eclipse mapping. Right. Again, we are using this effect where basically you have this planet with this blobby thing, right? This hot spot, and it's going behind its host star. Now, a couple ways to think of this. You can actually use the star as kind of like a knife edge. It will take different slices of the planet as it goes behind and then comes out the other side. You can actually then lay those over each other and reconstruct them to give you a temperature map. Okay, this has actually been done in the solar system to make maps of Pluto and other solar system bodies. Most of the way that we actually do it is we just look for these deviations in ingress and egress. So here is our ingress right here. So this is if it was a uniform temperature planet. You can see it most clearly in the egress right here. This planet is not uniform in temperature, and that's because we're probing that hot spot in particular. Okay, we can use those observations and make a map of the planet WST-17b. It looks nothing like Jupiter. If you take nothing else away from this talk, hot Jupiters look nothing like Jupiter. But we are able to measure the sort of relative offset of the hot spot on the planet to about 20 degrees. That tells us actually, you can then back calculate, given various time scales, how fast the winds are. So this is a way for us to actually measure the wind speeds in exoplanet atmospheres. They're on the order of 2 kilometers per second. We've done this also for HD 189733b. Here, we've compared our maps with the general circulation models. And what we're seeing is that sort of the location of the hotspot is very consistent with these one-time solar models right here. But the planet we're predicting is much cooler than what we're seeing. And so we're in the process of updating these general circulation models to figure out how to get that extra heating in. Maybe it's from magnetic fields or other processes. And so this is an iterative process where we have a map, we compare it to a GCM, we adjust the physics that's in the GCM, and then compare it to the map, et cetera, until we think we understand the physics that's shaping this planet.
You mentioned magnetic fields, how they seem.
So magnetic fields is like the catch-all, right? We have not definitively measured a magnetic field on an exoplanet.
That's
Okay, plain and simple. However, what we're starting to see from these maps in particular is that there's indications of chemistry, ion chemistry that requires magnetic fields. So, okay. All right, so a lot of the work that actually gets done in my group is building these types of models. We do both three-dimensional sort of retrieval exercises where we sort of make a toy model of the planet and then compare that to the data. Also run general circulation models that include a variety of physics and chemistry. Okay, so that's a whole other talk, but you can ask me about that later if you're big into general circulation models. All right, now we have time for our next contestant in the election day cycle here, and that's HAT P26b. This is our prototypical warm Neptune, all right? We, again, got transmission observations from 0.6 to 14 microns. We only got emission from 3 to about 12 microns, and that's because this planet is only 1,000 Kelvin. So there really was just no signal out here, and I wasn't going to waste a bunch of JWST time on something we weren't going to be able to detect. And so we have a complete transmission and then a partial emission spectrum of this planet. All right, so why this planet? Now, HAT P26b was observed with Hubble and Spitzer, along with these other beings that you see here. So HD 209458b, GJ 3470b. And what we've been trying to do for a long time now is to put these planets in context with the solar system. Now in the solar system we have a trend where we know with planet mass, there's an inverse relationship with the atmospheric metallicity, again, everything that's not hydrogen and helium. We think that, of course, this is because, Jupiter and Saturn, in the region that they formed, were able to gobble up more of the disk material, and so they look more like the star. Now here, these poor guys out here were a little starved because they were slow to start forming, and that's why they're tinier, but also why they're enriched in heavy elements. Okay? So the idea is if this is just how planets form, we should see the same trends in the exoplanet population. So far, we haven't been able to make particularly precise measurements, but we also aren't seeing a clear trend. P26b is interesting because it is roughly the same size as Neptune, but our initial observations indicated that it had a composition more similar to Jupiter. Okay? So we had to ask ourselves, why would that be? Now these were the first observations of P26b with HST. Again, this is 3 different, actually this is actually 6 different observations. So these are hard-fought, hard-won observations with Hubble, and then of course we have our 2 lovely points from Spitzer down here. But we were able to trace out water, which is good, which gives us some handle on the atmospheric metallicity. We also didn't see a big booming signal from CO2, so you notice the Spitzer point is down here, and so that sort of indicated to us that it was a lower metallicity. Now, here is our spectrum with JWST. So, turns out Spitzer was wrong. Sometimes it happens, it's okay. There's a big booming signature from CO2 out here. There's also a very large signature from, again, the sulfur dioxide. So this is the theme. We see sulfur dioxide literally everywhere.
I don't think of sulfur as being very common in the solar system.
It's much colder, so photochemistry is much more likely to be active.
So you think it's there, but it's like inside the planet or something?
Oh, these? So the sulfur, so SO2 is not the equilibrium sulfur-bearing species at these pressures and temperatures. And so in order to...
I guess the question I was wondering is, if just the absolute amount of sulfur, you have to have a certain amount of sulfur to have SO2.
Yes,
And
so
is that sort of a reasonable amount?
yeah, so these are also tied together here. So this is a big booming CO2 signature, indicates high metallicity. And so you have quite a reservoir of non-hydrogen and helium elements, but you also have photochemistry happening here. The prediction from basically our photochemical kinetic models was that it shouldn't be able to maintain staying in SO2. You're supposed to just like change into it and then change back into whatever it was before. But what we're seeing is that there's a significant amount of it there, which means it can persist even at these 1,000 Kelvin temperatures. Yeah. The other thing we were looking for is methane. So this planet is, again, around 1,000 Kelvin. That's the transition when we go between carbon monoxide and methane. That's sort of...
Is this a lower temperature planet than the previous?
Yes, it is. So 1,000 Kelvin. The other one was 1,800. So we expect actually there'd be more methane in this planet. All right. So turns out this thing was probably not as simple as we thought it was going to be. We thought we'd get a nice, just simple metallicity measurement. All would be well with the world. What we did find, however, is that with our JWST observations, and again, here are 2 different reductions, that's why you have 2 different posteriors, that we are getting a very supersolar O to H ratio. So this is actually somewhere in between Neptune and Saturn in terms of metallicity. And it's actually, I mean, it's in agreement to within a few sigma, but it's in tension with what was predicted from the Hubble and the Spitzer data alone. All right. But this places it back onto that line. So it actually puts it back onto that mass metallicity trend, which is good. Suddenly the universe works the way that we thought that it worked. The other thing that we're seeing again is this interesting chemistry. We've detected CO2 to a very high significance. Again, this is something like 30 times solar. We've also detected methane, which you don't see much of in exoplanet atmospheres. And this is probably tied to the fact that this is a subsolar abundance. We're seeing a huge amount of SO2. This can be photochemically destroyed. And so what we're seeing is basically tracers of a lot of photochemistry and quenching happening in this planet's atmosphere that models did not predict beforehand. All right, I'll go through this one real quick so we get to the last contender in our election. This is the emission observations of HAT P26b. I'm not going to show you a spectrum. It's not that interesting. However, what I do want to show you is this is one observation with JWST using MIRI. Okay. This is 8 observations with Spitzer that didn't get you anywhere near the precision that you were able to get with JWST MIRI. And so we had been banging our heads on trying to get emission measurements from planets like HAT P26b, and it's mostly because this is a cooler planet, and so JWST is really allowing us to measure emission from much cooler planets than we were able to before. All right, so we've got all the data plus more UV and vis transits coming in. And we've combined this also with observations from what was the transiting exoplanet early release science. And again, I want to emphasize one of the things that we're seeing across the board is if you start to lay these spectra on top of each other, we have WST-17, which is around 1800 Kelvin, HAT-26, which is around 1000 Kelvin but much smaller, and WST-39, which is also 1000 Kelvin but much bigger. You really can't distinguish the spectra. They're strangely similar in a way that we did not expect, okay? And so this tells us something about the way that these exoplanets have formed and what processes are shaping their atmospheres. All right, I have to get to TRAPPIST-1 because that's everyone's favorite. So, yes?
Oh, just for those last 3 planets, what was the difference between the stars you were looking at? Are they all the same star?
So this is an FKK. None of them are particularly active.
Okay.
We stayed away from the active stars because they're hard.
This degeneracy also expected from the theory, like
No.
if you do simulation or anything? Okay.
So especially, we expect, if you just predict what you would get for these planets, WST-17 would not have this high of metallicity, okay? You'd expect it to be more similar to Jupiter. You wouldn't expect SO2 to be a prominent feature in any of these planets, honestly, because they're all 1000 Kelvin or hotter, which is where we think photochemistry isn't able to operate.
So the physics is incomplete.
Yes.
And what do you miss, you think?
So we're missing a bunch of chemical kinetic measurements. So I can get on my laboratory astrophysics high horse at some point, but we are basically just missing a bunch of measurements that allow us to understand reaction rates and opacities at these particular pressures and temperatures.
But from the theory side, you don't know what is the main physics or ingredients.
Well,
you can
I
add.
understand the physics.
Okay,
If I plug in the numbers I have, it doesn't give me this answer.
Okay,
Does that make sense?
okay.
Yeah. All right. Final planet. Everyone's favorite TRAPPIST-1e. This planet is basically the same size as Earth, basically the same temperature as Earth, equilibrium temperature. It sits in the habitable zone around its very nasty active host star. Okay, you can ask me about that later. Tiny little M dwarf, it's the same size as Jupiter, but this is one of our best hopes for probing the atmospheres of a planet in the habitable zone of their host star. And we made a whole bunch of predictions about what we might expect from this planet if it had an atmosphere similar to, say, modern Earth, okay? And so we focused on this region from 0.6 out to about 5 microns, hoping we would pick up some of these CO2 features and maybe some methane features. Now, before we did this, let me tell you more about the TRAPPIST-1 system. Apologies again. Star is TRAPPIST-1a. It's barely a star, 2500 Kelvin, okay? But because it's so small and cool, it does allow us to look at these, well, first of all, discover and then study in detail these planets. B is the closest one. It orbits the star every 1.5 days. H is the farthest away. It orbits the star every 20 days. E orbits the star about every 6 days. And so you have lots of opportunities to study it as it goes around the host star. The hardest thing about this system is trying to get them in isolation, right? These planets are all whipping around all the time. You don't want their transits on top of each other, okay? All right, so with Hubble, we did some precursor work. There's a whole story here that I could go into. Hubble was not the ideal observatory for this, and we got a little greedy and decided to try to capture multiple transits all at one go, and we also operated during the SAA crossing. You can ask me about that later, which caused the telescope to have to go into this gyro-only mode. So our pointing wasn't very good, but despite all of that, we were able to actually extract some very rough spectra of all the planets in the TRAPPIST-1 system. And from this, we knew that they didn't have sort of large hydrogen-rich envelopes, which I guess shouldn't be too terribly surprising. These planets don't have primordial atmospheres, okay? So their atmospheres have either evolved, just like Earth's atmosphere, over time, or they don't have atmospheres at all. Now, here are our observations from JWST. Much nicer, you can actually see the transit by eye. All right, so a couple of things going on here. All right, let's play a game. Ready? What's this? Looking over here.
Spot. Flare.
It's a flare, that's right. So, this star is incredibly active. There are flares literally everywhere, okay? But we only got one. Other people who observe the TRAPPIST-1 system have been a lot less lucky than us. They have flares in the middle of their transits and everywhere else. All right, the other thing going on here. One of these things does not look like the other. Which one is it?
Blue one starts later.
Aha, yes. Blue one starts late. Why does the blue one start late? It's keeping you awake. What was that? No. Okay. So the way that we've measured the masses of these planets is not using radial velocity. We've measured the mass of these planets using something called transit timing variations. These planets are in such close orbits to each other, they're constantly tugging on one another, which means that you have variations in the center of transit time. And so we got 3 transits right near each other and then one that was farther away. And this information was actually used to refine the orbital ephemeris for the whole system in a recent paper. Okay? All right, so I'm not going to show you the spectrum right now. Senator Lockner-Key at the moment. But what I will tell you is that what we learned from doing these observations led to a Cycle 3 large program where we decided that we wanted to get both TRAPPIST-1e, which seems to have a hint of something in its atmosphere, we're just not sure what yet, and TRAPPIST-1b, which we're pretty sure doesn't have an atmosphere at all, and that's from observations that were taken with JWST that seem to indicate it has a temperature that is consistent with an atmosphere-free day side. And we can use that, then we have this bare rock and a potentially not bare rock observation all going across the same part of the star. And we can use that to do sort of a divide and conquer, right? We can divide out the signal of B, which should in fact be a flat line, and anything that's left over from E is indicative of a planetary atmosphere. So these observations are ongoing. I think we have 3 out of 12 that we're going to get, so stay tuned there. All right, so thank you for bearing with me on the 130 hours of observations I just ran you through. Now is the time to vote. All right, do you want this to be like a heads down vote or?
No.
Okay,
Double blind.
double blind. All right, we'll go backwards. Whose favorite planet is TRAPPIST-1? Whoa, we got 4. Oh, 5, see, Julian. All right, how about HAT P26b, our warm Neptune? 1, 2. Why HAT P26b? Speaks to you. Oh, no? No. All right, why HAT P26b?
I think everyone talked about Jupiter,
What did it say?
It's not a hot Jupiter. Fair enough. All right, whose team wants 17b? See, TRAPPIST-1 always wins. It makes me sad. We have measured literally nothing from this planet.
That's great. It's more to discover.
I know. But it does hold a lot of potential, which is why I continue to look at it, even though it really frustrates the hell out of me. Even when I'm looking at planets like WAT 17b that are giving me this booming signal. All right, so thank you for participating in my vote, and I will take any questions.
Okay, questions?
Is there only one of the TRAPPISTs that doesn't have an atmosphere or some number?
So all of the planets in the TRAPPIST-1 system, let me go back to that figure just so I can talk about them.
Sorry.
No, it's okay. planets in the TRAPPIST-1 system have been looked at with JWST. Interesting story is that we decided that C was the community target, and so none of the GTO teams touched it. So there are a lot of programs that are looking at C. Those observations seem to indicate that C also is not consistent with a strong or thick atmosphere, basically. It's not as conclusive as B. So B has a very solid conclusion that things just too damn hot for it to have any air recirculating heat from the day to the night. All the rest of them at this point are presenting various features that no one is willing to stand forward and be like, yes, it's a planetary atmosphere. And so that's in part why we were able to get basically another 100 hours to look at the system so that we can keep going down to precisions needed to say something definitive about the planets. But, you know, we'll see. It'll be interesting because, you know, from a planetary atmospheric evolution perspective, if none of them had atmospheres, that tells us something about how planetary atmospheres form and evolve, especially how they are blown off in these systems, and maybe M dwarfs are not a great place to look for life. But if it turns out that many of these planets in fact have atmospheres, then we have a new angle to start to play in the life game.
But if the star is so cool, why aren't they stripped of their atmosphere?
Oh, it's very active. Burping stuff all the time. Any questions?
What's the base of them?
Would simultaneous observations of the star help determine, like we took spectra at the moment of
That it's transiting?
yeah.
Yeah, so we called up our friends at various ground-based facilities, and we had monitoring during our observations of what the star, photometric monitoring.
Gotcha.
So we were able to at least put those observations in context based on the brightness levels. So
Okay.
that's basically it. Yeah, ground-based spectra are not probably going to get you much more.
Okay.
I'm just curious, what was the sort of origin or basis of the artist renditions?
Oh, for this? So this is,
They're very specific.
they are very, and they're actually very well informed. So Robert Hurt, if nobody knows who he is, he works at IPAC, is actually an astronomer artist. So he has a PhD in astronomy, but does mostly art. And so these were actually all derived based on using actual sort of physical intuition and talking to astronomers. He talked to me about it. And that's part of why, say, F right here has this like ocean that's exposed and then everything else is frozen out. It's right on the edge of the habitable zone, and we think that they're tidally locked, so they're facing in, and so the only part of the planet that would be able to maintain liquid water would be on that day side.
Like the green one, G.
This one is basically just like this is the biggest one, so it's like the Neptune of the bunch.
Why green? None of our solar system planets are green.
Well,
are
so so our ice giants are blue because of methane, right? That's because they're at a particular temperature. This one's hotter than our ice giants. And so it could have any number of features. I think these were supposed to be from various aerosols or photochemical species creating a green heat in the atmosphere. All right, happy to take any other questions. Okay. I know this is very far afield from what you all do
I
on a
have
regular
just
basis.
just a more general question. So
Yeah.
when you try to fit to the spectra, what do you vary in the models?
So we vary the atmospheric composition. So each species is allowed to turn individually. So you can change your water, your methane. So we end up putting in something like 30 different chemical species. We also, for the emission, we vary the structure of the PT profiles, the thermal structure. For the transmission, we tend to focus on isothermal
So
structures.
how many parameters?
So we end up having something around 30 parameters on average.
What did you say, 30?
And they're all important?
Yeah.
And they all change the spectrum. So then from the slide you showed that there is this degeneracy between these different planets in their spectra. Does that mean we need to have a different set of observation or different metrics to discriminate between these different planets, or
Well, I don't
what
think
does that?
I don't think it's actually bad that they're the same. That's just not what we predicted.
Okay.
Okay, so what it's pointing to is a consistent formation mechanism.
Okay.
So that these planets, even though they're all different sizes, perhaps all formed at the same region of the disk, and therefore inherited these various components. The SO2 stuff is just, we do need to actually update our photochemistry models, figure out why they wouldn't have predicted what we're seeing. But because they all have the same metallicity, it doesn't really, actually, it's not a bad thing.
Are these all neutral chemical models, or do you have ions?
We have ions. Yes.
Can you go back to the slide with your different models for the surface of this planet? Where do you derive those from?
Which models?
The
The pictures?
yeah.
These?
Yeah.
So this is, of course, a gas giant, so these are, just basically photospheric pictures of where it's emitting most of its energy. So the top ones are from an ultradimensional circulation model. So we made a model of the planet, put all the physics and chemistry that we thought was important in there. It actually only includes equilibrium chemistry, so we don't have photochemistry and other stuff in there. These models down here are the ones derived from that eclipse mapping. So we use a combination of basically spherical harmonics to fit to that deviation and ingress and egress that gives us sort of this very pixelated rudimentary map. But the fact that they're actually even vaguely similar is quite nice. The GCM's not totally wrong.
Can we expect life in these planets?
Oh, these planets? The hot Jupiters, probably not. There, of course, is a lot of discussion within the exoplanet community about some of these Hycean worlds, these sort of sub-Neptune sized things that could have these supercritical water layers in their atmosphere where maybe life could exist. And this is one of the first sort of biosignature detections that not everyone believes, but we're starting to see, again, these disequilibrium chemistry species popping up other places. And so there's a big push to start to think about life, maybe not as we understand it here on Earth, and to consider the broad range of planetary environments where it might evolve.
So do any of these objects have moons?
No. So the search for exomoons has been going on for a long time. And in part, remember, these are in very close orbits.
Yeah.
So if they had moons, they probably got ripped off during whatever violent encounter got them to where they are today.
Okay. I think we had plenty of questions. Let's start. So Nikole is going to be here 6 or so, right? So feel free to sign up and meet and join for dinner if you can.
Yeah, if let me or Sultan or I know if you're interested in dinner.
You guys gonna come to dinner too?
Nice.
No?
I think he's struggling a little bit, but.
Something to distract me, but yeah, we have
No?
to.
All? Dinner?
Well,
No?
since
No.
his former advisor.
Election day.
You going to vote?
My brain. So at least he can.
Oh, you should cut that, huh? You should cut